gotten your stuff out. A couple quick things. The answer key for the problems I gave you on Friday is now posted. There was one sort of problematic problem that you'll see in the key, but that you can obviously view that whenever you've completed it, or if you have some that you have questions about, and let me know if there are questions about that. Tomorrow, I'm going to give you guys a new packet with the practice questions from Question Bank that covers the whole topic, including the stuff we're going to do today. And I will make sure that I get these slides posted at the end of today. I actually changed a few things between first period and now so that could get hopefully a little bit better understanding of some of the stuff we're talking about today. So we only have a few things left to cover in this topic. One of them, we're going to start with this concept of metallic character. This is something that we've talked about metals and nonmetals. The metals are over on the left side of the periodic table, and the nonmetals are up in the top right corner. Most of the periodic table is metals, but what makes something a metal versus a nonmetal? And what it really comes down to is the fact that metals are going to lose their valence electrons to form positive ions. Nonmetals are going to gain electrons to form negative ions. And so all of that comes from the trends in the Coulombic forces and the effect of nuclear charge, in ionization energy, in electronegativity, and electron affinity. All of those trends create a situation where we get more metallic as we go down from the top to the bottom, and we get less metallic as we go from left to right, or more metallic as we go from right to left on the periodic table. Okay, so down in this bottom right corner, we have the lowest ionization energies. We have the lowest, excuse me, electron affinities. Apologies. Lowest electron affinities, electronegativities. And so this is where we have the elements that are going to be most likely to lose electrons. Up in the top here, we have the elements that have the highest ionization energy, electronegativity, electron affinity. So they're going to be the ones most likely to gain electrons. Okay. So when we talk about metallic character, that's pretty much what we're talking about. So the most metal is down here is francium. All right, and that also has to do with the reactivity, which we'll talk about in a minute. But this informs how these elements are bonding, and that's really the next topic. But it's important. It informs the next couple of trends, how the atoms of an element bond together. And so, even though this picture is showing different, mostly showing different elements bonding with other elements to form compounds, I want you to think about it in terms of having the same element bonded to itself or bonded to another atom of that element. There's sort of three main types of bonding. We talk in honors chemistry quite a bit about covalent and ionic bonding. Covalent bonding in which both atoms have a high electronegativity. Both of them want to take electrons in, and so neither is going to give them up, so they share them instead. Ionic bonding in which one element has a low electronegativity, the metal, and another element, the nonmetal, has a high electronegativity. So the nonmetal is just going to take an electron or a few electrons from the metal and create that positive and negative ions, which then are attracted to each other through those Coulombic forces. So we've talked about those quite a bit. What we don't spend a lot of time talking about in honors chemistry is the metallic bonding. When we have metals, a bunch of metal atoms all together, what we end up having is all of those atoms losing their valence electrons to become positive ions, and creating this lattice structure of positive ions, and then all the electrons that they've lost just kind of floating around in that area. And it's the attractive force between the positive ions and the sea of delocalized electrons that creates the structure of a metal. So I kind of drew it up here, but I have some other pictures in a minute. And the strength of the metallic bond is going to depend on the charge and the size of the atoms. Okay? So if I have something that is a smaller atom that has a smaller number of energy levels occupied, then the forces of attraction between the protons in the nucleus and those delocalized electrons are going to be stronger. If I have a higher charge, so we talked about these forces being affected by distance, how far away are the valence electrons, or in this case, the delocalized electrons from the nucleus, and also the charge. If there's a higher charge, then we're going to get a stronger force of attraction. So both of those things play into the strength of metallic bonding, which we'll talk about more in a second. And then there's also, not really, this slide says types of chemical bonding, but intramolecular forces is really not, they're not considered to be a chemical bond exactly, although at some point when you get to that, the threshold between a covalent bond and hydrogen bonding, things can get a little bit fuzzy. But essentially, we've got in intramolecular forces are when we have separate atoms or molecules where there's a polarity, a slight partial charge. And that can be permanent or it can be temporary. And that makes molecules stick together more or less. And that is also going to affect things like melting point and boiling point. Okay, so we have to kind of think about all of these things together in order to understand the last couple of periodic trends. And this is just some pictures of sodium metal bonding versus aluminum metal bonding. You can see that the aluminum has more electrons in the C because it has more valence electrons than sodium. It's going to lose all of those electrons to that sea of delocalized electrons. And so you can imagine that the forces holding this together as a structure are a little bit stronger in the aluminum than they are in the sodium, right? There's also some elements, particularly carbon and silicon, that form something that is sort of in between a metallic bond structure and a covalent bond structure. They're covalent bonds, but they create these giant networks. So think about diamond, and actually many other versions of carbon where we have pure carbon together, making these big networks of bonds. And this is just a picture that could be either diamond or it could be one of the forms of silicon, forming these tetrahedral arrays, this big network. And that creates something that is stronger. It's a stronger structure than either the metallic system or individual molecules sticking together, all right? And then we have other elements where they're nonmetals and they either form small molecules, so phosphorus, sulfur, and then also the diatomics, like the 7 diatomic elements, including the halogens, are going to form those two atom molecules. And so these are small molecules. They still have some intermolecular forces between them, but they're pretty small compared to the giant covalent structures. And then when we get to the noble gases, we're talking about single atoms that aren't bonded to anything else. They're just floating around independently by themselves. Okay. So thinking about all that, hopefully, will help make a little bit more sense of the last two trends that we're going to talk about. So we're going to start off with melting point. So this is page 16 on your study guide has a really crappy picture, which I'm sorry, you can sort of barely read it. It did not print well, and it really didn't copy well. So apologies for that. But you'll see that the melting point trends are different from any of the other trends we've looked at. And the way I remember this is that melting point makes a mountain peak in the middle of the period. Okay? So it goes up and then it comes down. And the reason for those changes, the reason for those increases and decreases within parts of period 3 in this case, come from the differences in bonding. Okay, so our sodium, magnesium, aluminum are going to be forming metallic bonds. The silicon is going to be forming giant covalent structures. The rest of them are going to be forming small molecules or single atoms. All right, so that's going to affect how this, how the melting point works. Because remember, melting point is just the temperature at which we go from a solid to a liquid. So a solid, we have all of our particles fixed in place relative to each other. They're still moving unless we're at absolute zero, but their movement is restricted. They're in a set location relative to the other particles. When we go to a liquid, when we melt something, we break down some of that structure. We break down some of those forces holding those particles in a particular place, and we let them, they're still touching each other, but we're letting them flow and move past each other. We're giving them translational motion, not just vibrational, rotational movement in place. Okay? And so the temperature at which something's going to melt depends on how strong the forces are holding it in that rigid, solid structure. Okay? If we have very strong forces, very stable structure, then it's going to take more energy. We're going to need a higher melting point. If the structures are weaker, it's going to melt more easily at a lower temperature. And so as we go across period 3, you're going to see this increase within the metals, and then you're going to see a peak at silicon, or if this is period 2, at carbon. And then you're going to see a big drop off, and then sort of a minor decrease going down for the rest of the period. Okay? And then we're also going to talk about going down a group on different sides of the table, because of the different types of bonding, the effects of going down a group, of getting larger atoms, is going to be different when we're talking about metals versus nonmetals. Okay? So this trend going across is just, we've got metallic bonds, sorry. We've got metallic bonds holding the atoms together. Here we've got giant covalent. And then over here we've got small covalent. So small covalent molecules. So when we talk about the melting point or boiling point of these covalent molecules, we're not talking about breaking the chemical bonds. We're talking about breaking up the intermolecular forces. Okay, we're talking about keeping the Cl2s or the S8s or whatever from breaking apart the things, the attractive forces that are holding them loosely together in either a liquid or a solid form. In the case of melting point, in the solid form. Okay, so that trend in that difference in the bond type is going to tell us how, relatively speaking, how the melting point is going to look. Thinking about going down a group, if we look at group 1, you'll see this on study guide page 18, where it talks a little bit more about the group 1 elements and sort of trends within group 1. And they're mostly things that we've already talked about, as far as decrease in ionization energy, increase in atomic radius, the general trends that we've talked about. As we go down group 1, our melting point gets smaller. Our melting point decreases. So it takes less energy to melt cesium than it does to melt lithium. And notice that we're not including hydrogen in here because hydrogen is kind of not really part of group 1 as far as its chemical trends other than the valence electrons. Okay. So why would we see, as we're going down, thinking about the metallic structure, the structure of a metallic bonding system, why would we see a decrease in melting point going from the top to the bottom? Why would it be easier to disrupt that solid structure at a lower temperature? Patrick? Exactly, yeah. We've got bigger atoms with essentially a smaller effective nuclear charge in the sense of there's more shielding between the nucleus and those valence electrons. And now we're talking about not valence electrons, but that sea of delocalized electrons that the valence electrons have turned into. And so as we go down a group, we're not changing the charge because everybody in group 1 is going to have the same +1 charge, but we are changing that distance. And so we are weakening those Coulombic forces and making it easier to break down that structure. Okay. Oops. Okay. So the larger the atom, the more occupied energy levels we have a weaker attractive force. It takes less energy to separate those positive ions from each other and have them still be able to flow as a liquid. Now, we also, did I put this in here? Yeah, I did. Okay. So I put this slide in here to talk about like the relative strengths of the metallic bonds. So yes, as we go down, the metallic bonding gets weaker because we have larger ions, bigger volume of the electron cloud, just not as effective at holding together. So it takes less energy to melt that. But we do have an increase in the melting point going across within the metals, because as we go across from, say, sodium to magnesium to aluminum, we have a bigger charge. So we have the same number of energy levels, but we have a bigger charge. So this increase here is due to the bigger charge of those positive ions. Okay? So when we're just going across a period, the increase in the charge of the ions is going to increase the strength of that of the metallic bonding. As we're going down, it's going to get weaker because of the bigger distance, the more electron shells. Okay, in group 17, we see the opposite trend. In group 17, this is on page 19 of your study guide, going from fluorine down to astatine, we see an increase in the melting point. So we have these small covalent molecules, or in the case of the noble gases, single atoms. And as we go down the group, it gets harder and harder and harder to separate them from each other, to take them from a solid phase into a liquid phase. And you can actually see this in terms of the group 17 elements. Fluorine and chlorine are gases at room temperature. Bromine is a liquid iodine is a solid, and acetine is a solid as well. So we're going from very volatile, very easy to, very low melting point and boiling point, and then gradually increasing as we go down. Why would that be? Why would these molecules stick together more as we go down the group? This is kind of going back to your intramolecular forces from a while ago. Okay. Remember that these, particularly the group 17 elements, these are all diatomic. Okay, they're all going to have two atoms stuck together. That's how they're going to exist as a pure element in nature. It's never going to be just one fluorine atom unless it's bonded to something else. So if we have pure fluorine, it's going to be F2. If we have pure chlorine, it's going to be Cl2. Remember that the intramolecular forces are forces of attraction between molecules that are based on the same Coulombic attractive forces that we've been talking about. The opposites attract. All right, except here, we're not talking about something that's necessarily a positive or negative ion. We're talking about partial charges. We're talking about it's a little bit more negative on this side and a little bit more positive on this side. And there are some molecules like water that are very polar and permanently polar. They have a permanent dipole. And that's going to affect the way water hangs together, the surface tension, capillary action, all kinds of things about water. But even in something like an iodine molecule, where we pretty much just have two atoms stuck together of exactly the same element. There's no electronegativity difference here. There's no reason for one side of this molecule to be more or less negative. This would be considered a nonpolar molecule. However, we have to remember that the electrons are constantly moving around. All right, they're not stationary, and they're not even stuck in particular orbits around the nucleus. Okay, so certainly the shared bonding electrons are going to be moving around between these two atoms. And even some of the other electrons can potentially be moving around at any given time. They're not locked into one space, okay? They're in orbitals, but it's not like, they're not like little boxes where you turn the key and it never comes out, okay? So we've got the possibility, even in a totally nonpolar molecule, for the creation of a temporary dipole because some of the electrons, a few more of the electrons happen to be on one side of the molecule and create a slight negative charge on that side and a slight positive charge on the other side. And this is just a temporary, instantaneous, momentary thing, just for a second, okay? Not even a second. But if that happens, then if there's this unequal distribution, that creates this temporary dipole, which can then, if there's a molecule next to it that also has a temporary dipole, or creates a temporary dipole in response to the presence of this unequal distribution and says, ooh, my electrons want to be over here. They don't want to be close to this big concentration of electrons. Then it becomes a ripple effect. And you get something like iodine, with a completely nonpolar molecule, being solid at room temperature. Because there's enough of, even that temporary dipole can be strong enough to make those molecules stick together. Okay. If you have larger molecules with more electrons, that dispersion force, if we're talking about the London dispersion forces, that dispersion force gets stronger. So the bigger the molecule, the more electrons are moving around, the more chance there is of having more of them on one side than the other, and the more chance there is of having it be a bigger temporary dipole. Those forces are going to be stronger. So that's why we see this trend down group 17 is the larger molecules gives us stronger IMFs. especially when we're just talking about dispersion force. Okay. So the forces holding the molecules together are stronger. It takes more energy to separate them, to turn a solid into a liquid, to then turn a liquid into a gas. So two different trends on different sides of the periodic table because of the structure of the substance, of the pure substance. Okay. And you can see this. This is a graph where we're going through the first 20 elements with melting point in green and boiling point in purple, blue, whatever this is. And that you can see that, it periodically changes. So we have the same mountain peak in the middle of period 2 that we have in the middle of period 3. And then it kind of gets a little bit messier from there. But you won't be asked anything past period 3. Most of the melting point questions are going to be about elements in periods 2 or 3. Okay. Okay, the last thing that they want you to know about is also looking at period 3, looking at those elements, but now talking about, and this is a little bit annoying because this really should be in topic 4, which is about bonding, but talking about the oxides, so the compounds that are made between the period 3 elements and oxygen. Oxides are very common because there's oxygen in the air. So every element is, exposed to some amount of oxygen, unless we're talking about, anaerobic conditions in volcanoes or deep sea vents or something like that. Everybody has some oxygen exposure, and so and oxygen's pretty reactive, so oxides are going to form pretty readily. So if we think about going across the period, this graph shows the electronegativity. We already know that electronegativity goes up because of the increased number of protons, the increased effective nuclear charge. If we think about those period 3 elements, sodium to chlorine, and we think about relative to oxygen, oxygen's electronegativity is about 3.4, depending on what table you're looking at, but your data booklet says 3.4. Okay? And so you can see that there's a big difference in electronegativity between oxygen and the metals. Okay? Big differences in electronegativity lead to bonding where the more electronegative element yoinks the electrons away from the less electronegative element. So this is going to create ionic bonding, ionic compounds. Okay. Whereas over here, on the nonmetal side, we're going to have a situation where the oxygen is going to combine with the nonmetals to make covalent compounds. Because we have much smaller differences in electronegativity here. Neither side really gets to win, gets to steal the electrons, so we end up with covalent compounds. And then you get this weird thing going on with silicon, where it basically takes that crazy tetrahedral giant covalent thing and adds oxygen to make silicon dioxide. Okay? And so this is also going to be a giant covalent structure. So the type of bonding within these different oxides is going to determine, again, much like with the melting point and boiling point of the pure elements, it's going to determine their properties. And one of the properties that they want you to know, and of course, we haven't covered acids and bases yet because that's topic 8, but this is an illustration of how everything in chemistry depends on everything else, and there's really no perfect way to divide things up or sequence them. These oxides have different acid-base character. So sodium oxide and magnesium oxide, those are both ionic compounds, and those compounds are basic. The silicon dioxide is very weakly acidic. As that giant covalent compound. And our Covalent compounds with oxygen act as acids. They have acidic character. So again, this is our ionic compounds and sort of aluminum, although we'll talk a little bit more next topic about the aluminum oxide and its sort of specialness. We've got our giant covalent, and then we have our covalent over here. This is still ionic, it's just a little bit wonky. So the acidic character goes with the structure. The ionic oxides are going to be basic, the covalent oxides are going to be acidic, and it's going to kind of trend in that direction. I don't want to go too far into this. I'm going to keep this slide in, and it'll get posted with the rest of the slides. But there are some questions where they ask you to predict the reaction of these oxides with water and what that's going to produce. And I don't want to go super into that right now. I think I want to circle back around to this when we do acids and bases and we talk about those reactions of acids and bases with water. I think it just makes more sense. But I'm leaving it here so that you can see it. So, and then it's basically the same stuff that we've been talking about. Now, aluminum has this term called amphoteric because it is both. It can go both ways. So if you take aluminum oxide and react it with an acid, it will act like a base. If you take aluminum oxide and react it with a base, it will act like an acid. So it can go both ways. It's kind of in the middle, right? And this is page 17 in your study guide. I thought I put it up earlier as well, but in case I didn't, all of these are that this is basically the part that you need to know for this topic. I won't ask you questions on this topic's quiz about predicting the reactions. Okay. All right, so this takes us to one more paper one question. I will give you a bunch more question bank questions tomorrow. So it says elements X, Y, and Z are in the same period of the periodic table. And these are the relative sizes of the atoms. Now, before we even look at the rest of this, what can you tell me about the relative positions of X, Y, and Z in that period? Are they in the correct order going from left to right? Are they in reverse order? Is there some other order that they should be in? Just being told that they're in the same period and their atomic size is represented by the circles. Edward, you look like the wheels are turning. It's correct, yeah. So this is the largest atom is going to be on the left side. The smallest atom is going to be on the right side. Okay, so it just goes X, Y, Z across. And then it asks you which trends are correct. And it asks you ionization energy, effective nuclear charge, and least to most acidic oxide. So take a minute to think about who's got the highest ionization energy, who's got the highest effective nuclear charge, and who has the most acidic oxide out of these three elements. Who's going to have the highest ionization energy? Okay. Z. Yep. So we can get rid of choice D because that's not correct. Who's going to have the highest effective nuclear charge? Yade. Remember, they're in the same period. Not sure? Z? What did you say? Z also? Yeah. Yeah, so effective nuclear charge also increasing as we go across. Who's going to have, so that gets us, gets rid of these two. Who's got the most acidic oxide? Also Z. So even if you weren't sure about the oxides, you'd have gotten yourself down to, 2 of the answer choices out of the 4. So this is going to be our correct answer. I'm going to post these slides. It's going to include this slide here, which is one way of representing on your blank periodic table the trends that we've been talking about. Okay? This one has all arrows pointing in the direction of an increase versus all arrows pointing in the same direction and then describing whether it's increasing or decreasing. There are many ways to do this. I just wanted to point out that, I've got arrows going across, arrows going up or down. I have a couple spots where my arrow, for example, ionic radius, gets smaller within the anions, it also gets smaller within the cations, and there's a jump, so you want to make sure that you are somehow recording that. I've got the melting point and boiling point facing in to make that mountain peak for the melting point. Reactivity is also going to be different. There's not specific questions about that on this topic, but generally speaking, the nonmetals are going to be increasingly reactive as we get to fluorine. Metals are going to be increasingly reactive as we get down, give them more metallic character. So reactivity is kind of going along with metallic character. The less metallic you are as a nonmetal, the more reactive you are. The more metallic you are as a metal, the more reactive you are. And I'm going to post some videos of reactivity differences going down groups 1 and group 7. So I'll put this up in Canvas for tomorrow. All right, guys, thanks very much.